Testing. Everyone, just glad you're here. We're going to start in a few minutes.
It's pretty full. Okay, he says he can hear machine sounds. Is that what yeah, okay. We are good. Yeah, he's going to have to play it off the line. Okay. Could be a little more volume. Should get down and play out here, do some break dancing.
And then just wait for answers.
The end of the talk. You'll figure it out. I'm much more notoriously just like asking questions.
Do you want a microphone to drop? Yeah, we'll give you a mic box.
Yeah. Most questions, here's a microphone.
You guys got food, right? That was something that's hard to come by.
I didn't grab food.
No?
If I did,
Do you want some water or something?
I got a couple of.
Okay, great.
If I did food, it would be hard to talk right now.
So maybe after this, decide. I was going to say, like, just get the session of food and do so.
Put together a small plate for you. I feel a little bit over time. I mean, I have a little bit of experience doing the stage management stuff, but it's like also I have a kid and like getting here on time is like so stressful. It's like especially when like I felt bad. Do you know how talk? Jay, he like introduced himself, and I was like, do you want an introduction? I can just do it.
This talk's recorded, right? Like, we'll get that.
Okay, so as long as he was, I was just like, was I just not here in time? I don't know. Yeah. That's fine. I mean, he was thinking like, we're gonna make it this way. That's totally fine. That's really the personalities. Have fun. That's what it's about.
All right. Welcome, everybody. It's my pleasure to present Vikasha as our third early career keynote speaker. So he is a co-founder of MyoLab and also an adjunct professor at Carnegie Mellon University. He received his PhD from Washington University. He has worked at numerous places, including Meta AI, Google Brain, OpenAI, and yeah, he's also been a co-founder of many of the frameworks that we all know and love, such as Mujoko. And with that, I'm going to hand over.
All right. Can you all hear me? All right, perfect. Let's get started. First, thank you for giving the honor to just come and speak to you over here. It's just a pleasure. As I was building the talk, I thought, what should I talk about? And this was the immediate moment. It's like, I'm going to share with you 3 of my own robotics moments and how it eventually bled into something I'm going to talk about today. Right? So first of which is this first explosive video of first hardware experiment I ever ran. My heart imploded after this experiment. Eventually, things worked out just fine. Second, how something I watched in the childhood, Tailspin, I don't know, like show of hands, anyone know, watched this? Yeah, yeah, very cool thing. It was one of the favorite things, how it connects to robotics. And finally, one evening, I'm going out for a dinner and how that connected into something that I profoundly use in robotics career. So I'm going to talk about what is the future. Future is anything but optimal, I believe, and I'll slowly expand on what I mean by that. And when it comes to robots and future, first, how we got here. So we as humans are very curious individuals. We are goal-directed, and we seek optimality. We're not truly optimal. We pretend that we seek optimality, and we wanted robots to just do exactly the same, be curious, be goal-directed, and act optimally. And that was the first foray into how robotics started. Strategy, be optimal, design optimal hardwares, design optimal controllers, act optimally. And this led to quite a bit of improvements. Like we can see very impressive robotic skills. That's how we initially started. Get everyone motivated. Robots are coming and they're going to do amazing things. How it went in practice is we somehow tried to define and capture optimality using reward functions, time-dependent reward functions. Then we leaned on literature of control theory to design optimal controllers that maximize this reward. Obviously, there was a bunch of assumptions to how to do that, and the assumptions being that we have fully observable state, and we have access to the state. The second, we have stationary dynamics, and we have known and access to the dynamics. So equipped with this optimality principle, I also designed a very cool hardware. In 2.5 seconds, it's going through its digit, and this is my first optimal control experiment running on the hardware, which you all saw right now. Just exploding. All right, my heart imploded, and I'm like, okay, I'm going to try harder and get this to work. We tried really hard to build good state estimators, good estimates of the model, and neither of them were perfect, and the search for optimality over there took a step back. And my aspiration of this building a very dexterous hand was, okay, I don't have good state estimates. I don't have good estimates of the model, and especially in stationary setting, how am I going to even go to non-stationary setting? Very, very bad situation. Then came the era of reinforcement learning, and everything magically started to come together. We can run reinforcement learning in the real world. We can do things like domain randomization. You can run reinforcement learning over a couple of domain randomized environments. This transfers to the real world, and everyone is happy. Some people are not happy because it doesn't work for them. But maybe we are looking at the wrong place. I want to maybe highlight something else that is going on, that it is not reinforcement learning, but the setting has changed. That instead of looking for one single optimal move, we want a policy that is valid in a much wider distribution. And this policy, sometimes we induce in the domain by training directly on the hardware, or we induce that policy off domain and in a much wider setting and make sure that domain or the distribution aligns with the real world. So that is what I think is the key. It's not the optimizer, which we usually talk about, because what can here happen is I can switch the optimizer to a trajectory optimization, and I can still do the exact same technique. So usually when people say RL, I want maybe to have a second thought that under the hood something else also changed. So the design principle of being optimal now changes to I want to be robust to much wider distribution. And that's basically what started making things work. All right, so this is all nice and good. I adopted some of these principles, and these are the changes that happens in the robust control era, that we started to think about robust control. First thing, let go of pure information about the state, think directly in the observation space. Second, model estimates are never going to be perfect. Work with learned models or model-free. Third, instead of looking for 0 point around the optimal positioning, look and identify for distributions and try to stay in good part of the distribution. Finally, local controllers that are around the optimal point got replaced by global policies that are valid throughout the entire state distribution. And finally, which is the key of what most of my talk is going to be about, the optimal behaviors, the search for optimal behaviors got replaced by search for robust behaviors while being in distribution. So when I thought about solving robotics, this was the initial picture. There is a cost function, reward, I want to be on the top of it. That felt like the problem, and state estimation issues felt like I need to find that 0 point. And the failure initially, which I thought was state estimate, was actually because I was just going out of distribution. It was not that my policy was bad. Policy was good enough. State estimates was good enough, but as I took more and more action, I was just diverting away from it. So this view of robotics changed into this view of robotics. It's a pursuit of distribution, and the policy's job is to keep me in the distribution all the time. That was my change, my aha moment when things somehow, some flip switched in my brain. So the lessons from here are, the job of the policy is to push the system towards good distribution. Expose the policy to wider and wider distribution because you don't know where you're going to end up being. And that is basically what's going to fuel the robotics. How do we expose things to wider and wider distribution? And finally, and this is a little bit on the technical side, we fundamentally switched the underlying problem we were trying to solve. So initially, we were trying to assume true access, and the pursuit was towards optimal control. We switched the problem to a distributional MDP. There is a distribution of states, distribution of actions, and we want to be in the good part of the distribution, and the strategy was to be robust. This is underlying problems changing, not any one particular algorithm solving it. And this is also highlighted in Professor Thomas's talk. Basically said that once you have formulated the problem right, all the methods of solving the problem applies. Now, second part of my talk, how do we find this wide distribution? Because that seems like the outcome of the first one. All right, simulation, big domain gap, seems like problem. Real world, limited data seems like a problem. Aspirations are high that we want robots to actually work in everyday life on every situation. But even single task setting, in all true generality of the single task setting, the way Jitendra mentioned it, we can't do it. So here is a new setting, a reduced setting. I'll try to make my point using this. That let's just say a robot knows how to pick up this bottle, and the job is that I want this robot to pick any bottle in the world anywhere it can find it. And if we can do that in the true sense of this is a truly general robot, maybe in one instantiation of it, right? But here is another kicker. All of these bottles are not real. And even for like half a second it was able to fool you, the question becomes, why can't I fool the robots about the same? And this is basically the concept of data augmentation. And it's not a new concept. In the field of vision, we have used it over and over, and usually it leads to a lot of cropping, rotations, etc. And if you want to think about it, is what are they doing and can be adopted? So they are just inducing invariances to shift rotations, color perturbations, etc. So it's all a game of invariances and how you can induce that invariances. And we, in the field of robot learning, said, yes, we can also do that. We started building scenes in physics simulations. We started randomizing those scenes. We started visually randomizing those scenes, and it started transferring. But another problem happens that the scene creation is expensive, and it does not scale to the real world, and real world is too diverse. So the invariances we actually want is not in the simulation. We want these invariances to work in the real world. Question is, how do we find those invariances? And this is where I fooled you first, right? Can we take a simple image, use generations of those images, and bring the invariances of the real world instead of the simulator? That is a key insight over here, that this problem of simulation-based data augmentation should get replaced by generation base, and it solves two problems, that it brings in the invariances directly of the real world, not the simulator. And finally, we are going to test under hard situations like real world situations. So let's just perform these experiments. I'm going to quickly do these details. How do we augment everything? We just basically take the objects, we change their textures, we add some background noises, we basically give distractor objects, and that exactly is what's happening over here. So problem setting is we collect 10 demonstration on a very clean tabletop settings. We do augmented generation of only the state space. This is important. We only augment the state space, and the augmentation cannot be any augmentation. This augmentation has to be such that the augmented image has to be valid for the same action. That is the key over here. You have to ensure, and then we just train the policy. You can do supervised learning. You can train any mechanism that you would like. And I want to, again, underline, highlight. I did another game over here. I changed the problem that we are solving. That instead of like solving the MDP problem for the state action distribution that typically imitation learning will solve for, I actually augmented the state distribution. I augmented the goal distribution while ensuring that my action distribution remains the same and the state action tuple remains valid. That's what happened over here, and you could have really used any method to train the policy and it will do better. Again, the second lesson over here is usually we are progressing by changing the problems that we are solving. That is the key. We usually talk about algorithms, but there is also something happening under the hood we should pay attention to. Here is basically, I'll let the video play, 10 demonstration on very clean tabletop surfaces. We just do imitation learning from data augmentation, and everything that you see on the right is zero-shot generalization. And you can see these distributions are very, very different because the demonstrations were collected in a very simple scene. And it's quite amazing, and we were surprised by how good this was. And it works like reasonably well in a wide variety of settings. So let's look into what actually was happening. The first is we are going to show different kinds of augmentations we did. Right? First bar is no augmentation, and the second bar is random augmentation. So we already see by augmenting the state space while the same action is valid is actually giving us some benefit. But what really surprised us is the augmentation helps, but this generative augmentation really, really helps. It helps such that it's very hard to understand why it helped so much. So the question became, why did this help? And the answer for this is hidden basically in the question of like tailspin. And this point was made by a colleague of mine, Arvind, and it's like a beautiful argument. It's like, why do we understand cartoons? There is big embodiment gap. For God's sake, this is a bear walking like a human, has 3 fingers, can manipulate everything, but we understand it. There is a big embodiment gap. We still understand it. Why the reverse is not true for robots? There is a big embodiment gap, but there is evidence that we can understand across the big embodiment gap. And a common way of making this also argument is we get a lot of instructions that are in cartoons and we can understand them back. Right? So here are the takeaways and what we learned from this. First, that large models on which I'm using for augmentations are trained on internet scale data. And what they have is world priors. And when you augment, you bring in those world priors back into your state action distribution almost for free. Second is these world priors can be induced despite of the embodiment gap. Example, this cartoon. And the third is the state action tuple that was initially considered to be very, very closely related can be decoupled. We can really just augment the state while without touching the action, and this decoupling allows us to induce much wider distribution. So the game of wider distribution now begins. And you have any favorite method of yours to train the policy, this will apply, this intuition will apply. And this was reinforced by Danfei also in his talk, that it's a game of finding where the bigger data distribution is. His argument was embodied human distribution. I'm going to go even one step further. Any data is good because it has world priors, even if it's not about the humans. So the role of off-domain data set now starts in robot learning. The whole principle is train big models. Now it's called foundation models. We started before it was called foundation models. And then use these foundation models to bring in real-world priors of the world into your existing data distribution, state action distribution. And that is going to expand what the policy knows, expand the invariances it is exposed to, and it's going to become more and more valid in a much wider distribution space. All right, everything nice and good. We have one task, somehow pick in place kind of a task. We can solve it in a much wider settings. We show some. The next pursuit begins how we can go towards a universal agent. Right? This is the ultimate goal of everyone. And by that, what I mean is we want a single agent that is capable of multiple skills. It knows how to use those skills for multiple tasks, and it works truly in unseen settings. Right? Somehow, Jitendra gave a very clean definition of what he means by that. I'm not going to expand more. I'm largely in resonance with what he has to say. So here is my third intuition, my third story. One evening, I'm going out, and a plan is to dress up. By show of hands, if you have to dress up, would you choose setting A to begin with? All right, someone? Setting B to begin with. All right, majority of the people, right? So here, the act of dressing up is a very articulate task, involves full body movements. And if I can do that, I'm called a smart individual capable of understanding the world. But here was my realization. That I was called smart, but I only was able to act smart because a lot of people started from growing the cotton to making the fabric to stitching it up to making the houses to making the spile and eventually putting it in a nice organized way for me to do 2 steps in life and call myself intelligent. That was a big gap, right? 90%, 99% of the work is in going from A to B or going from scratch to B, and I had the audacity to call myself smart by just wearing the clothes that were hanging on the hanger. And are we doing something like same in robotics? Can we somehow shift all the problems ahead of time and then let the robots do a couple of the last steps, but nicely? That would be a good recipe. Implications of this essentially is the making decision is easier with better representations, right? It's a better organized closet. I can get up ready much faster. These representations can be acquired out of domain, which is nice because robot data is hard to collect. So out of domain data sets, great. Humans do that a lot, motor babbling, sports, etc. We prepare ourselves without knowing what is coming in the future, and in the future we have to do something, we quickly just do it snap, right? And this is where parenting kicks in, right? For a large amount of time, you're just helping the kid pick up these representations, so later in life the kid is going to succeed. It's a hard thing to do, and we might have to do it for robots as well without much of a return in the beginning. And finally, this is the key point. The need for a robot action data set is heavily reduced now because you might be able to push a lot of the learning lessons off domain, right? So a lot of people now who are going very hard into collecting large, massive robotics data set, I might want you to think about this point a little bit more. The first point of need for structure was also reinforced by Georgia, which was very, very nice. All right, so this realization by 2021, the way I formulated it with a couple of colleagues at Meta was that we want to do data-driven learning, which majority of the learning has to be off-domain and ahead of time. That means learn from simulated data sets, learn from human data sets, learn from any robot data sets available. But the problem is we need to some point have to fix the domain and distribution transfer to the robot embodiment. This will be paired with interaction-driven learning, and this is where the grounding to the robots happen. It has less data, so that it lacks diversity, but the good part is it's interaction-rich, so you can actually quickly fine-tune and find your anchor in the bigger distribution. And the whole goal is going to move the center of gravity as much towards the left side, which is towards the offline side of things, right? And this was 2021. foundation model term wasn't coined, we built a lot of representations. But since then, a lot more people have built these kinds of representations. I don't think I'm saying something new. I don't think I'm saying something common. I would expect majority of you to believe already in what I'm saying. Right? But here is a couple of interesting things. With so many representations out there, the question is, what is the right foundation model? That's where I'm confused now. And this somehow will resonate. If you know the story, it's good. Otherwise, it's the blind and the elephant. Depending on what part of the elephant you touch, you think it's a different thing. And of all the representations I showed you, there is an organization in this chaos. It starts looking like this. Some people call, I'm going to solve robotics using LLMs. Some people are more along the lines of human embodiment is the right way to do this. Some people are along the lines of train multimodal representations across multiple modalities, and that's going to help it, right? But my question is, which is the elephant which we are all looking at? And the way I define this elephant is what I call it is a representational MDP. Let me explain a little bit more what I mean by that. A representational MDP is a representational viewpoint of the robotics decision-making problem. Where we initially start with this MDP tuple, what we are all doing is building structure of each one of the elements of the tuple. And each one of these structures, latent codes, are essentially all of these foundation models. These are a couple of visual foundation models. Some we have built, some across the board. Here are some world model style models. Here is some where you generalize multimodal goals. Here is something along the lines of value functions, reward functions that we need. But there are also embodiment-specific models, which is also nice. Because initially we thought like, okay, we can't even do embodiment transfer, but there are good embodiment-based models that are coming. Essentially what is going on is we are subscribing to the mindset which Jitendra was also saying, that we as humans are building a lot of representations and we should use them. And these representations are acquired ahead of time and then use them when the time is right. Don't wait to learn representation when the task is in front of you. So we are fundamentally solving yet different problem again, right? We are acquiring these representations ahead of time, and same old recipe of solving MDPs will apply again to this new setting. And the good part is we can solve interactive MDP solution in domain with much smaller data sets. But training these distributions with wide distribution stiff is the offline process. It takes a while. So let me give you my instantiation of this solution. I think all of us should have our own instantiation, but just give you an example of representational MDP can be solved and it can lead to good things. So we created a RoboSet. It's a multi-skill, multitask, multimodal data set. Because what we have learned so far is the action distribution is the key. No one can help us with the action distribution. So for your robot, you have to find your own action distribution. So it was very important for us to make sure action distribution is multi-skills, multitask, multimodal, etc. We expanded the skill distribution as widely as possible. It has 12 skills, but the data set is very, very small. It's only 7,500 trajectories. With that small data set, here is a glimpse of a single universal agent and what it's capable of. All of them are unknown settings that the robot has never seen before. It's a single model, and notice the kind of behavior that you see, how smooth it is. It's very nimble, it does make mistakes, it does interact with everything, and it recovers and nice. Question, what is this agent? How does it work? How it came into being? It is a single goal condition policy, conditional language goal. It is capable of 12 skills, and we have tested it across hundreds of unseen situations. How did we build it? We first took that small data sets. We followed the exact same policy of using foundation model to augment the data set. I'm going to talk a little bit more about this in the next slide. And then we basically used a pre-trained language model to actually express goals in language. And then we extended our previous work on action chunking transformer to multitask setting, where the multitask conditioning is coming from language queries. And that is our training phase. During the inference, we just get 4 of these images from the camera. We basically ask user, what do you want? User said something, action chunking process happens the classic way, temporal aggregation that goes to the robot, everything is good. Here is a little bit of a detail on semantic augmentation and what is nice and interesting about it. So we take one image, we essentially segment out both the robot and the object, and then we randomly pick a couple of other objects in the scene. And we augment both these things, both the object that you're interacting with and a randomly picked object that you are not interacting with. What ends up happening is these are both the same demonstration from two different viewpoints. This is what the video starts looking like. And we are just using standard text-to-image and painting models to do that. This is what our model sees. And it basically is saying is I'm exposing state invariances to you in which the same action distribution is valid. That's all this is doing. Here a couple of details is there is no temporal consistency between any of this. Every frame is independent. There is no viewpoint consistency between any of this. Every camera has its own augmentation, and it doesn't really matter. These are some other examples. So the key takeaway over here is with no additional human or robot cost, we are able to multiply the data just using compute cost. Here are generalization, because that's where the key lies. Starting with small, simple object level generalization, lighting level generalization, going harder into background and distractor objects level generalization, going into new task, new object level generalization, and finally even new scenes, new situation generalization. What was interesting is here is all the success percentages stacked on one top of each other. So MTAct ends up doing really, really well. You know, as the generalization gets harder, the success reduces. But compared to RT1 or BET, which we know has been very, very strong contenders, it doesn't really work over here as nice. And the question becomes, what the hell happened? And the point here is that we are able to do 5.3 times better. Question is why? And the answer was someone over here, that our data set is so tiny that some of these other models are not even able to take any leverage out of them, because they are really trained on large data sets where they are able to do good. So the key takeaway here is even with small data sets, because of these augmentation and world priors, you are really able to outperform some of these big models. Right? So if you carefully think of the problem, there is a lot of leverage, a lot of juice available everywhere else. Here's a second insight, and my last one for this result, is as we increase the number of augmentations, the generalization ability increases even more. So as you bring in more and more world priors, you're actually able to improve the generalization almost for free. The question is why, and the insight is basically hidden that we have a very high skill diversity. That means when you bake in invariances on the state, it latches on all the existing skills that is required to solve harder and harder tasks. And it hasn't plateaued. We have tried up to 7 per frame, but you could keep going over and over. Robustness of this agent is also very, very strong. So for example, this is one of the tasks, slide out the bowl from the toaster oven. Both the robot is adamant and the human is adamant against each other. You can kind of see the human being like very aggressive of not letting the robot succeed, and the emergent properties of the robot is kind of evident over here as well. This need for not being optimal and being robust to no matter what the world presents to you is also somehow now we can start understanding why the cost of hardware is going down, why on crappy hardwares we are starting to do better and better. We started on this intuitions in 2017. So for a really long time, we have been building policies on somewhat crappy hardwares, and now most of the convincing results are coming on low-cost hardwares. Right? And the intuition is now very valid and clear. What is happening is we are building invariances, we are letting go of optimal stance. We are trying to be robust to whatever the world presents to us. That also means invariances to the error in your system dynamics. You don't have to be repeatable. That need for a perfect hardware is not that aggressive anymore. With that, here are my final takeaways. Universal agents can be achieved, but the need is to expose the agents to wider and wider distribution. World priors can be baked using off-domain data sets, to improve this distribution. The state action tuple, which is considered the holy grail and tightly knit together, I think they can be decoupled to widen the distribution. Just have to be a little bit careful. And usually we talk about algorithms, but under the hood, I want everyone to also please consider that we are fundamentally changing different problems every day, and that is also leading to big transformation in why robotics actually is working. And finally, good enough has to be good enough. Yeah. Here is my final, a little bit philosophical take, is at some point we need to reach a minimal viability. So the stance has to be, do you want to build a pyramid by tiny bricks one at a time and eventually get to the top? It'll take a long time. This is what we are doing. Spinning small bricks, this doesn't work, I'm going to build this. This doesn't work, build this. No. Or do you want to just take a bunch of big olives, no matter what it is, and just dump them one on top of the other to get to the minimum viability as soon as possible with the same amount of effort? Now, choice of olives are yours. You could make skills, options, use cases, be explicit, be implicit. Those choices are totally yours. So here is my final. The future is anything but robust. It's a pursuit of anything but optimal. It's a pursuit to be robust. It's a pursuit to expose wider and wider distributions. With that, I just want to thank everyone who gave me the opportunity to speak on their behalf, all the collaborators, and all my advisors and mentors who have tolerated when I was wrong. I think it really helps. Thank you so much.
All right. Thank you very much, Vikash. I think we have time for a couple of questions. Oh.
Very nice talks, Vikash. So one question about your augmentation work. It seems like you could do this augmentation for pick and place kind of tasks. But what are your thoughts on going beyond pick and place?
For the second robo-agent that is way beyond pick and place, all the augmentations are also valid over there. So I think it can be extended very easily. Even for the second GenAug work, I didn't cover it, but in the paper, we have like natural, like full arm behavior cloning results as well.
Thank you.
Great talk. So my question is, how many skills do you think we need for robots?
I think that's a Jitendra's question. But I do believe the number is rather small. I think Jitendra went to 50. I will even stick to 10 to 15. Okay. I think 10 to 15, I think you would have robots. If we have 10 to 15 skills, we would have robots in homes, but have to work perfectly.
And so what would be those skills?
I am more a fan of implicit, but I think we have seen Cordelia and others make also arguments about explicit. I'm more than welcoming. I'm personally more excited about the implicit ones. So there's no definition, no boundary for me.
Thanks.
Question. Yeah. Hi. Hello.
Where am I looking?
Here, right in the front.
Okay.
Are we to understand that we can train a robot to open the microwave door or the toaster door in any setting with just 20 demos and the rest of augmentation?
I don't think 20 demos are going to be enough. And the question is, you need to expose wider and wider distribution. For certain tasks, you can just do it much more automatically in the augmented way that I showed you, but I don't think other tasks where things are more complex, the same strategy would work. For example, kneading a dough requires much more action distribution that needs to be represented well. For that, you might need more demonstration. But the recipe would work. It's just that you have to find your balance about what the number is going to be.
Your recipe mostly focused on the environment changes that you are able to bring in through augmentations, right?
Right.
What about just the problem of opening the door? Let's say we don't bring in that. Mm-hmm. That itself has a lot of variability and a lot of interest, right? What's your take on it? Like how?
Yeah, for that, the action distribution has to be wide enough. And the question is, do you bring in the action distribution using RL as a framework and let the exploration do the job? Or do you want to do it as an imitation learning problem where you collect a large enough action distribution represented in your imitation learning data set? Those choices are available for the users to choose.
Thank you.
All right, last question there.
Yeah, hi.
Hi.
Really wonderful talk.
Thank you.
I'm also wondering about this data augmentations. How do you make sure that they don't create non-causal scenes, so stuff that where the actions would not be weighted? And do you think we need more, like maybe causal inference or this kind of methods to scale this to really complicated scenarios, or do you think we have everything?
I will quote Jitendra over here. These methods have a way of washing these outliers out. We have found non-meaningful scene generation. For example, in a computer scene, when you ask for, hey, put mouse on the left, you literally get mice instead of like electronic mouse over there. And it works just fine.
All right, thank you very much, Vikash. Let's give him another big round of applause. We are now going to switch over to the last spotlight session. So could the speakers, especially the first 5, come down here?
Sure, yeah. Is everybody here? Are they all lining up? Are they all lining up? Okay, cool. Sure. All right, so I'll be your session chair for this next session. Just a quick reminder of your spotlight instructions for all the speakers. There are going to be 60-second spotlight videos that run automatically, one after the other. Please, the 5 speakers, queue up. Your order will be given by your paper number. Thank you. The 60-second timer will be displayed at the bottom of the screen. When that red bar appears, you have 7 seconds left. The next person needs to come up when the red bar appears. And yeah, the next speaker just gets up. Please hold your applause until the end of the entire session. All right? Go for it.
Hello, everyone. My name is Carl, and I'm here to tell you something that many of you know, which is that robot evaluation is not fun. Robots break all the time, they take forever to run, and in the end, the whole thing is not even reproducible. And this problem gets worse for generalist policies. So in our project, we're trying to solve this and make evaluation simpler. Our idea here is that we take these very popular real-world benchmarks and we translate them into equivalent simulated benchmarks. This allows us to run evaluation at very large scale, across many, many different environments. And we find that in the end, when we compare the evaluation in simulation with evaluation in the real world, we see very strong correlation across a bunch of different foundation models people have published. We also find that the same holds true when you evaluate across a bunch of different robustness cases out of distribution scenarios. And if you want to learn more about how the whole thing works, please find us at our poster right outside the door. Thank you.
My name is Tyler Lum, and I'm excited to present Day3. Day3 is a pixel-to-action policy that performs robust and dynamic grasping in the real world. It's safe, fast, and continuously reactive. It's all trained entirely in simulation with a geometric fabric controller. We first trained a teacher policy that learns with reinforcement learning and privileged information. And then we train a student policy that learns with noisy depth images and online dagger. Day3 is deployed zero-shot in the real world and achieves fast and reactive behavior that generalizes to novel objects from a single depth image view. What's the geometric fabric? Here's the equation. It's great, but I'm out of time. Come to the poster and check out our website. Day3, thanks you for your attention.
My name is Jiafeng Cai. Six-of-grade detection is a foundation skill for robot to grade objects. Given the single viewpoint clause, the grade detector predicts the suitable position and orientation for the real world. For the gripper, well, the goal is to enable robots to grade anything. A key challenge is the lack of sufficient training data. Simulated data offers a scalable and effective solution, but it faces the challenge of the large gap between simulation and real world. This gap is caused by the camera noise. In our paper, we present a grasping dataset in simulation to train grade detector and propose a real-to-scene framework for syslog grad detection to bridge the gap. For more detail, welcome to my poster.
Hello everyone. Today I'm going to introduce our work on occupancy flow prediction. Our aim is to achieve joint 3D occupancy and occupancy flow prediction with a temporal image sequence. Previous work relies heavily on expensive 3D occupancy annotation and bounding box annotations. However, our method utilizes 2D rendering supervision from RGB images and optical flow cues, which are convenient to obtain. To achieve this goal, we introduced SDF-based rendering supervision, and we also designed a novel attention-based temporal fusion module and dynamic disentanglement strategy. We conducted extensive experiments on KDMOT and new scenes datasets. Our method achieved comparative results even with other methods. Thank you for listening. If you have any questions, please contact us.
I'm Meenal, and I'm excited to present Fetch Bench, a simulation benchmark for robot fetching. Grasping is crucial in manipulation, yet evaluations often overlook the role of environment in it, which involves approaching the object, grasping it, and redirecting to the free space. For this task of fetching, lack of a benchmark has made it unclear whether existing methods can handle complex scenarios. We propose Fetch Bench, which features procedurally generated complex scenarios inspired from real-world scenes. We evaluate 7 algorithms across sense, plan, act agents and end-to-end behavior agents trained on Fetch Bench trained dataset. Surprisingly, we find that among all baselines, 20% success rate is the maximum we achieve. Further, with systematic applications using Oracle components, we find that grasp prediction and motion planning remain the key bottlenecks. For detailed analysis on our results, please visit our poster number 5. Thank you.
Hi everyone, we present Sonic Sense, object perception from in-hand acoustic vibration. Our robot has 4 fingers and a contact microphone is embedded inside the fingertip. This allows our robot to collect acoustic vibration signals during the interaction between the robot and the objects. From the unique acoustic vibration signatures, our robot is able to differentiate the geometry and the inventory status of the object inside the container. To overcome more challenging object perception tasks, we collect data over 83 real-world objects through a sequence of tapping motion. Based on the collected contact point and acoustic vibration signals, our robot is able to infer the material composition of the object, reconstruct the shape of the object based on the spark contact point, and re-identify the object based on a small number of interactions. To learn more about our project, please come to our poster section. Thank you.
Hi everyone, I'm Roger from Stanford University. I would like to start with the question that, is digital twin necessary for robust policy learning for sim-to-real transfer? And is it possible to avoid manually defining digital twins, which takes a lot of human efforts? To answer these questions, we propose the concept of digital cousins, which are virtual assets or scenes that share similar geometric affordances as real-world objects, but do not explicitly define them as digital twins. For automated creation with digital cousins, we propose ACDC, which is a fully automated real-to-sim-to-real pipeline that can generate digital cousins from a single RGB image without additional human efforts, and training policies on digital cousins in simulation that can be deployed in the original real-world scene. Experiments show that policies trained on digital cousins are more robust than policies trained on digital twins in both sim-to-sim and sim-to-real settings. We have open sourced our code, and welcome to chatting with us in the poster session. Thank you.
Hi, I'm here to present our work, Promptable Closed-Loop Traffic Simulation. Let me first introduce what our model, ProSim, do. So ProSim focuses on promptable closed-loop traffic simulation. For normal traffic simulation tasks, given an input map and initial state, ProSim outputs traffic scenarios throughout for all the agents unconditionally in a closed loop. In our task, we're also given each agent a multimodal prompts, which include action types, goal points, schedule points, or even text. Then ProSim can faithfully condition all the agents based on which prompts they are given and rule out the scenario in an interactive way. In this fashion, users can use ProSim to easily create a lot of interesting traffic scenarios that runs in closed loop and interact with each other. Please come to our poster number 8 for more information. Thank you.
Hello, I'm Xiang Yang Li. I'm from Institute of Computing Technology. Today, we will introduce our work for visual language navigation. In this work, we design performance, but difficult to develop most robust, which didn't come from with private RGB camera due to their high cost and large size. Our goal is to design a VLN system that enable molecular robots to achieve near parametric performance. In this way, two challenges must be addressed. For identifying transfer area, we propose a method to predict navigable repoints around the VLN system. For represent symptomatic and spatial relationship with the parametric, the scientific field is utilized to represent the environment. So we achieve better performance. Thank you.
Hello. We present a planar symmetric SO3 representation for learning graph detection from Uben by Toyota. So many grapers, especially Parallel grapers, have planar symmetry. That means a grasp both and another one with 180-degree flipped will result in a same grasp. However, such grasps have a bimodality, and that is hard for a neural network to learn. So in this work, we present a novel rotation representation that can represent a pair of two symmetric grasp poles in a single 9-parameter set by leveraging the Bingham distribution. We experimentally confirmed that without our rotation representation, sometimes the grasp yield angle takes a clearly wrong value, which is between the two valid grasp poses. But in our rotation representation, such failure mode doesn't happen anymore. So if you're any interested, please come to the poster number 10. Thank you.
Hi, I'm Lantao Liu, and I'm recovering from a cold, so I might be coughing. So one challenge for RL is to generate suitable environment to co-evolve with the policy training. And our works uses a pre-trained diffusion model as a terrain generator, but we guide the generation process to produce appropriately challenging environments. This is done by selecting the forward diffusion step and adding noise in the underlying training environments and fuse them proportional to the potential contribution to the policy improvements. So we compare our method with benchmark environmental generation methods, and the key takeaway here is that our method is superior in training the challenging unseen environments. So we also tested our diffusion model with real robots in diverse challenging terrains. And I have more videos to show in the poster.
Hi, everyone. We present Splat Mover, a modular robotic stack for open vocabulary manipulation. Splat Mover uses a 3D Gaussian splatting representation to perform multi-stage manipulation tasks. Our method consists of 3 modules. First, AskSplat distills semantic and grasp affordance features into the 3D scene, which are useful for object manipulation and segmentation. Second, CSplat enables real-time scene editing using 3D semantic masking and infilling to visualize the motions of objects and to update our representation for the next manipulation stage. Finally, GraspSplat utilizes these other modules to propose affordance-aligned candidate grasps for open-world objects. Altogether, this enables robust, multi-stage robotic manipulation, which improves on existing baselines. Please check out our website, and I look forward to seeing you at the poster session. Thank you.
Hi, everyone. I'm Eric, and I'm here to present Tax3D, our work on non-rigid relative placement. Recent methods for relative placement have made tremendous progress towards sample-efficient manipulation policies, but are often in practice limited to rigid pose prediction. How can we extend relative placement to deformable non-rigid manipulation settings, which are ubiquitous in the real world? We propose a simple formulation to model deformable transformations through dense cross-displacement diffusion. Given segmented point clouds of an action object A to be manipulated and an anchor object B, we initialize displacements as Gaussian noise, compute object-centric point features, and diffuse over displacements to predict a final action object configuration. Our method generalizes to unseen object instances out of distribution scene configurations and multimodal placements, achieving superior generalization performance when compared to a state-of-the-art end-to-end visual motor policy. If you want to hear more, come check us out at Poster 13.
Hi, I'm Thies, and we at TU Vienna developed a modular motion planning framework where we can encode task constraints with an LLM, and with a custom path planner based on convex sets, we can have then secure and constrained motions. So for example, here we transfer a filled cup, where we need to keep it upright to fulfill the task successfully. So on the left, you see what happens without the upright constraint, and on the right, you can see what happens with the upright constraint. So without the constraint, you can see that we have spillage, and this is undesired. So with our planner, we can avoid this. In our second example, we have wiping a table where we are constrained on the table, but the other motion is unconstrained. But we still have a smooth motions throughout all the tasks and have thus very good constrained motion planning. Thank you.
Hi, I'm Yishu. I'm presenting our work, Flowbot HD. The work is done in Carnegie Mellon University. Ambiguities are common in manipulation. For example, when a door is fully closed, there is natural uncertainty as to how it opens. And when a door is open to certain angles, it might become severely occluded and barely visible. These ambiguities poses challenges to deterministic policies to make precise and consistent predictions. Therefore, we propose a 3D diffusion process to model the multimodal distribution, and we incorporate history through a history injection mechanism to provide additional context during occluded observations. Our system is called Flowbot HD, and in both simulation and real-world settings, we demonstrate its ability to manipulate a wide range of articulate objects, including a custom-made door that can be configured to open in 4 different configurations. If you're interested, please come to our poster. Thank you.
Hi, I'm Abhijat, and I'll be talking about our work where we explore how we can use driver gaze to model their situational awareness. In the video here, a driver is pulling up to an intersection with a van in the opposing lane, turning right. They look towards the van's future path, but fail to notice a pedestrian in that area, which leads to them almost running over the pedestrian when they jaywalk into their path later. We contribute a novel way to get ground truth labels of driver awareness in our VR driving simulator. In contrast to existing techniques which require a pause during simulated driving and explicit probes about driver awareness, our method produces denser and more continuous real-time labels without interrupting driving, and a formulation as a segmentation task produces better precision recall and inference time complexity. Come check us out at poster number 16. Thanks.
Hello, my name is Aiden Curtis. Today I'm going to be talking about our work called Trust the Process. So VLMs and LLMs have recently shown a remarkable ability to zero-shot solve novel tasks specified in natural language, such as draw a circle or align these blocks in this particular line. However, many modern methods fail to consider real-world constraints, such as grasp failures, obstacle collisions, kinematic infeasibility, or physical stability. Failing to consider these constraints can lead to either the LLM suggesting completely infeasible actions or actions that, when executed, result in catastrophic failures. Our solution explicitly reasons about these constraints by solving a constraint satisfaction problem that is proposed by the LLM as a subspace of the solution space. And so we're able to use this to do stuff like drawing stars while avoiding collisions in a cluttered scene. And we have lots of other tasks in cluttered scenes. Come check out our poster. Thank you.
I'm Yichun, presenting VoxAct-B, voxel-based acting and stabilizing policy for bimanual manipulation. Bimanual manipulation tasks are challenging due to high-dimensional action spaces. Prior methods train policies on large data sets or explore primitive actions. So how can we design a simple, efficient method without relying on primitive actions? We propose VoxACB, a language condition voxel-based method that leverages vision language models to prioritize key regions within the scene and reconstruct a voxel grid. Our method learns from multi-model data, which consists of left-acting and right-stabilizing demonstrations, as well as right-acting and left-stabilizing demonstrations. We use language instructions and VLMs to determine the roles of each arm, whether they're acting or stabilizing during inference. Our method outperforms state-of-the-art methods such as ACT, diffusion policy, and VoxPoser. Come check out our poster at number 18 and website for more details.
Hi, I'm Terry. I present our work about multitask robotic manipulation. The task setting is to train a single policy for robots to follow the language instructions to handle multiple tasks via the imitation learning. The previous method did not focus on the relationship between the language and the corresponding visual inputs to differentiate the multitask representations, as well as enhancing the recognition of movement trajectories across different tasks. So our method introduces contrastive imitation learning, which is implemented in the two aspects. The first is matching the vision and the language features of the different tasks. The other is to make visual features of different trajectories more contrastive. Our method has more discriminative representations and achieves good performance in both the simulated and the real-world experiments. So for more details, please come to see Hai in the poster 19. Thank you.
Hi everyone, this is Ziwen Zhuang, the author of robot parkour learning last year. This year we introduced humanoid parkour learning. This is the first humanoid locomotion algorithm that requires no motion prior, but achieves the state-of-the-art agility among current humanoid locomotion tasks. Using Perling noise terrain, we show that the training does not need any motion prior to achieve the various parkour tasks. We further show the safety awareness of our policy when facing dangerous obstacles, even when the operator tells it to move forward. We also show that our whole body control policy can be seamlessly integrated with mobile manipulation tasks by overriding the upper limbs action. We can achieve interesting playful tasks such as playing badminton. Please check out our paper at poster number 20. Thank you.
Hello everyone, I'm Utkarsh, and today I'm going to present my work on generative factor chaining. So solving long horizon planning is very tough because the search space is exponential, and we need to solve this constraint satisfaction problem. So we are proposing generative factor chaining, where we're representing state as a spatial factor graph and realize their temporal evolution by these temporal factors. And then, with our method, we can propose a one-stop solution to formulate task-level distribution as a composition of these spatial and temporal level distribution. Each factor is a diffusion model, which is trained for learning the joint distribution of each of these nodes of which of their interest is, and then we can just compose them together for multiple solutions of different long horizon plans. And we can solve these kind of collaborative task zero shot by just learning what we can have for each skill. Thank you.
Enforcement learning approach. Hybrid action space to facilitate free gate motion planning for hexapod robots navigating randomly generated plum blossom pile environments. We first address the complexity of multi-leg coordination in discrete environments by treating each leg of the hexapod robot as an individual agent. The motion of all legs is modeled as a Markov game with a specific state transition function determined by the proposed free gate transition feasibility model. Then, we propose the hybrid action space multi-agent soft actor critic algorithm capable of handling both discrete and continuous actions. To evaluate the proposed method, we use 3 different types of simulated environments and a real-world environment. The integrated free gate motion planning method based on hybrid MASAC, streamlining gate, center of mass, and foothold sequences planning into a single model. The success rate in most environments is close to 100%. Our future work will focus on training more robust policies and combining the proposed method with localization and map building methods. Thank you.
Hi, my name is Young-Gyo, and I'm presenting on behalf of my friends who couldn't come. So today I'm introducing a new benchmark called ByGym. And BiGym consists of 40 diverse tasks ranging from simple to complex tasks. And BiGym supports both RGB and depth camera input. And a very nice thing about BiGym is that we provide human-collected demonstrations that are multimodal and noisy, as in real-world robot demonstrations. And we evaluated both behavior cloning and demo-driven RL algorithms, and there's a huge room for improvement. So we hope that our new benchmark provides new research opportunities to the research community, and any suggestion, comment, contributions are welcome. So thank you for listening, and please visit our poster session.
Hello, everyone. Goal continuous reinforcement learning is cool because the robots can follow our arbitrary commands. But what's even more exciting is unsupervised goal conditional RL. We do not need lengthy hand-engineered URL functions, nor do we need hundreds of hours of demonstrations, which can save us a lot of hassle. Our approach begins with selecting the intrinsic goal that is temporally farthest from the states that we visited. Then the agent tries to move temporally closer to the goal. And finally, the agent further explores by moving temporally farther away from the previous states. By repeating this process, TLDR can autonomously navigate complex terrains and also discover effective goal reaching gates. Poster 24 on the second floor. Thank you.
Hi, my name is Balaj, and our work is called Point Patch RL. Point clouds offer many benefits for reinforcement learning over image observations. They make it easier to extract task-relevant object geometry, to represent occlusions, and also to combine multiple camera perspectives. Yet despite the vast array of architectures used in supervised learning, very few of those have been used as encoders in a control context. So we introduced Point Patch RL, a method for RL and point clouds that builds on the common paradigm of dividing a point cloud into overlapping patches, tokenizing them, and processing the tokens with a transformer. We then add a masked reconstruction objective that masks out some of these tokens and tries to reconstruct the missing points. Point Patch RL provides significant benefits across the 6 environments that we tested compared to image-based and point cloud-based baselines, and our policies generalize across object variations.
Hi, I'm Piotr Kicki, and this is our work on bridging a gap between learning to plan, motion primitives, and safe reinforcement learning. In this work, we want to solve a problem of finding a policy that generates trajectories which maximize the rewards while satisfying kinodynamic safety constraints. Our approach combines learning to plan, reinforcement learning, and motion primitives. Our solution, CNP3O, uses a neural network to generate trajectories that are smooth and they are executed in the environment. And based on the episodic PPO, we can learn based on these rewards and also based on the rewards from the constraints. And we show in the experimental setting that our approach outperforms existing solutions. It's easy to impose prior knowledge in that case. And also it transfers 0 shots to the real world setting in this air hockey scenario. Thank you for your attention.
Hello, everyone. My name is Yang Gao from EPFL. Today, I'm very happy to share our work about pre-trained model for human motion prediction. So this task can be treated as multi-model input and output. Specifically, in our model, we treat the input as historical trajectory, 3D to the post key point, and the bounding boxes, and we predict the future trajectory and the 3D post key points as output. So we first create a unified human motion data framework by merging 7 existing datasets. Based on that, we propose a pre-trained model with novel masking techniques. This model can be easily fine-tuned on different frame settings for trajectory prediction and post-prediction. Here is a brief visualization for the trajectory prediction on the NBA scenario and the post-prediction on AMAS. And we also try to apply the predictor in the robot navigation scenario. By using the predictor, the robot can reach the goal faster with lower collision rate. And welcome to our poster. Thank you.
Hello, everyone. I will present our recent work on robust manipulation primitive learning. The objective is to learn robust policies that can manipulate a wide range of objects with instance-specific optimal behaviors. But all the existing methods have their own problems. Therefore, in this paper, we propose domain contraction. It's a bilevel approach. The first step is to learn parameter-augmented policy using multiple models, and then the resulted advantage function is used to retrieve the parameter conditioned policy by making product with a rough parameter distribution. We validate our approach on 3 different context-rich manipulation primitives: hitting, pushing, and reorientation, with diverse physical parameters. The results showcase the effectiveness of using domain contraction to retrieve the optimal behaviors. For more details, please check out our website and talk with me in the poster session. Thank you.
In this work, we introduce a framework for teaching robots new skills through language and visual demonstration. In our approach, a set of large language and vision models are composed to synthesize code-based robot policies that generalize to unseen objects and environments. High-level structure is extracted from the provided demonstration using hand, object, and semantic priors. And to generalize skills to unseen objects and environments, features from an image diffusion model are leveraged to find corresponding structure. Goal poses are defined relative to this structure, and a collision-free motion planner is used to interpolate between poses. Our framework jointly reasons about the visual demonstration and any provided language instructions to produce skills that can exercise high-level logic like conditions, iteration, and segmentation. To learn more, please stop by our poster, number 29. Thank you.
Hello everyone, my name is Nico and I will present to you one policy to run them all. As you might know, reinforcement learning currently achieves state-of-the-art results in robot locomotion, but usually we train policies only for a single robot. This means whenever we have a new robot, we also need to train a new policy from scratch. But we would rather have a powerful general policy that can control all of them. Therefore, we introduced the Unified Robot Morphology Architecture, URMA. URMA is not a transformer, but it uses an attention mechanism to encode variable amounts of joints with unique joint description vectors. It combines this with general observations in a core network, and then produces the final actions by concatenating the latents with the joint descriptions again in our universal decoder. URMA is trained on 16 simulated robots with different humanoids, quadrupeds, and hexapods, and finally deployed on 2 quadrupeds known from simulation and one that we never seen before.
Hi everyone, I'm Patrick and I'll be introducing ResPilot. Human hands are capable of extremely dexterous manipulation, but existing retargeters fail to reproduce this functionality on robot hands, making it difficult to perform this complex in-hand manipulation. We address this by calibrating a retargeter to individual users using Gaussian processes and implement a shared control interface to aid operators in grasping objects. As a result, our retargeter enables operators to precisely coordinate multiple fingers simultaneously, letting them complete complex tasks such as transitioning between different grasps to use tools. Our retargeter also allows operators to pick up objects from the robot's palm and maintain a stable grasp even while reorienting the object with other fingers. Finally, our retargeter is also very precise, allowing the operator to pick up extremely thin objects like credit cards. This also allows them to precisely modulate forces they apply to enable things like controlled slipping. Please come check out our poster and website.
Hello everyone, this is Colin Yu from Georgia Tech. Let's talk about our paper Mimic Touch. So the first contribution of our paper is we only utilize tactile and audio feedback, which are without any visual feedback. And the second one is we utilize human play data to use the human tactile feedback and the human's dexterity. And to achieve this goal, we first need to crack human tactile demonstrations, and we use self-supervised learning to train the encoders, and we use non-parametric imitation learning to train the offline policy, and finally, we use RL to bridge the embodiment gap between human and robot. With this framework, we can show that the robot can learn human-like control-guided tactile strategy for insertion text. And we also do some zero-shot generalizations to different texts with different hold positions, different tactile angles, two-stage dense packings, the multi-materials, and also a simulated task. Please come to our poster session if you are interested.
Hi everyone, I'm Jonas and I would like to present our work on handling long-term safety and uncertainty in safe reinforcement learning. Safety is a key problem for transferring machine learning solutions in the real world. One major issue is that constraints are usually unknown or hard to quantify. While there are numerous safe reinforcement learning approaches that try to solve this issue, almost all of them are purely data-driven. Our approach, distributional ATACOM, incorporates prior knowledge in form of a affine control system, and we learn the constraint with a distributional feasibility value function. By combining these, we can handle long-term safety and uncertainty. Distributional ATACOM outperforms state-of-the-art methods in terms of safety while being competitive in performance. We're the only method that learns the active collision avoidance in the video. If you want to learn more, come to my poster.
Previous works addressing closed-loop control for non-prehensile manipulation rely on complex external perception setups that guarantee continuous object tracking. In contrast, we present an estimation and control framework that enables us to perform closed-loop, non-prehensile tasks with a simple onboard camera and leverage tactile sensing to continue solving the task during long visual occlusions. We first train a privileged RL policy in an environment without occlusions. By rolling out a wide range of optimal and suboptimal checkpoints, we collect highly diverse interaction data to which we add synthetic occlusions and noise. We use this data to learn a visotactile state estimator under a Bayesian deep learning framework to capture its uncertainty. Finally, we train an uncertainty-aware RL control policy using the learned estimator in the loop and deploy them with zero-shot sim-to-real transfer. If this sounds interesting, please come to our poster session. Thank you.
Hi, I'll talk about our work on text-based scene representation. So the key idea here is for very high-level reasoning, you probably don't need detailed geometry of the scene. So we propose to represent a viewpoint-centric scene representation as a database of viewpoints indexed by the semantic classes observed from a viewpoint. And we show that from this viewpoint-centric representation, we can recover object-centric 3D localizations. Besides objects, we can also localize rooms and locales affordances. And then lastly, we show that we can interface this representation with language models to this text-based nature to do useful ground navigation tasks. So for example, I can say, get me some tap water to drink, and given the scene context, the language model knows I should go to the sink to get some tap water. And then after it goes to the sink, I can say, okay, I don't like drinking cold water, can you please heat it up for me? And then the robot can go to the microwave to heat the water. And then I can also say, can you please go to the logo to take a photo of you for our lab? And our lab has a lot of logos because it's quite into self-promotion. So I can say, please go to the closest logo. And yeah, okay, please check out our posters.
Hello everyone, my name is Hao Jie. I would present imagination policy. So if there is a banana on the table, could you imagine the picture of grasping the banana by hand? And the fact is that if we have the mental picture, we already know what the action looks like. Inspired by it, imagination policy generates the point cloud of the goal state and then infer the actions. It also has the multimodal capability to generate different configurations with the same input. We formulate as a manipulation keyframe pick and place policy. It can generate the pick, pre-place, and place configurations, and then infer the actions. Finally, imagination policy is a multitask model handling various simulated and real-world experiments. Its sample efficiency and can achieve good performance within 10 demonstrations. Feel free to check out posters. Thanks.
Hello everyone, I'm Li Chuan Wang from Georgia Tech, and today I'll be presenting ACTAIM 2. So how can a robot interact with an articulate object without any groundings? As a human beings, we identify plausible actions like opening or closing drawers, each with a low-level action movements. So our goal is to enable robots to do the same, which led to ACTAIM 2. So ACTAIM 2 has been successfully deployed into this real-world settings, performing both sample modes such as opening and closing drawers without privileged prior informations. So it achieved this by creating a discrete representation of the interaction modes and generating corresponding low-level actions without privileged information. It generates across various objects. So the model has two parts, and one is this mode selector, which gives you a GMA distribution of this discrete representation of interaction mode, and also a low-level action predictor gives you precise trajectory. For more information, please come to our poster session. Thanks.
Hello, I'm Zhe Yu. So in this work, we aim at improving robustness against task-unrelated visual domain shifts in behavior cloning, like change of lighting, shadows, distractors, and backgrounds. So for generic behavior cloning policy that includes an image encoder and a regressor, we first extract saliency at the image encoder level, and the input saliency is normalized, then use it as weights to overlay the in-domain image with the out-of-domain image to generate the augmented image. So the proposed method scales to multiple camera views, various regressor types, and requires no architectural change or training objectives. And here are some demos. Thank you.
We are interested in the problem of gentle manipulation of tree branches. This is a challenging problem because tree branches are very hard to model. And as you move through the foliage, there is very limited vision. So we present our proprioceptive only policy, PCAP, which is model-free, vision-free, and we do not use any external tactile sensing. We train our policy for a reach task, and we observe that the agent deploys very novel emergent strategies to evade collisions and to minimize contact impact. Our policy works where baselines fail with very minimal contact ruptures. Most importantly, we can transfer this policy zero shot from sim to real to work on real tree branches. Please visit our poster number 39 for more details and some cool videos. Thank you.
I had to introduce GenDP, 3D semantic fields for category-level generalizable diffusion policy. In this work, we introduced a diffusion policy framework capable of category-level generalization. For example, we use these 3 shoes to train the shoe aligning task, as shown in the training demo. Our framework can generalize to novel instances with very different appearances and geometry, like high heels and slippers. Our method takes in multi-view RGBD observations and extracts 3D descriptor fields encoding high-dimensional features. Compared with selected descriptors from reference images, we obtain our semantic fields, which are then fed into diffusion policy to predict actions. Our framework pays attention to the subtle geometric details. To place the soda can lying on the table upright, it is necessary to know which side is the top. Certain details, such as the soda can tab, could help the robot to make decisions, which, however, is not obvious from geometric information. Our 3D semantic fields attend to such details to place the soda can upright without flipping it. Similarly, our approach can highlight the head of the toothbrush for toothpaste spreading task. Welcome to our poster session for more details.
Hi everyone, I'm Bikram and he's Asutosh from Oregon State University. We present you decentralized multi-biped control for payload transport using a carrier that is adaptable to any number of robots without retraining. Our policy takes in internal robot states, carrier commands, and robot relative position with the carrier and produces low-level action as motor set points. We train using IPPO across multiple environments, up to 3 robots, by randomizing payload masses and carrier shapes. Our simulation shows that, results shows that it's adaptable to any number of robots with random payloads and carrier shapes.
With additional training, the robots also are able to traverse challenging terrain and recover from instability. We deploy our policy on hardware with 2 and 3 chassis robot systems, with each running the same policy without any communication, and they can maintain the speed and height of the carrier as provided. Thank you. Come check out our poster and the project webpage for more videos.
Hello, I'm Andrew Lee from UC Davis, and I'm excited to share our work and track our new approach to enhancing bimanual manipulation. Bimanual tasks usually involve each arm performing virtually independent actions with minimal coordination, while also requiring more coordination at specific phases. Intract is a simple recipe for bimanual manipulation that makes sure each arm can function independently while synchronizing when necessary. The core of Intract is its hierarchical attention mechanism, which leverages dedicated CLS tokens for each arm. Through the selective attention process, these tokens can learn to pull the cues needed for synchronized action. Here are the visualization of the attention made to the CLS tokens. During the coordination phase, attention shifts to prioritize these special tokens to generate precise coordinated actions. We have tested our approach across multiple sim and real tasks and showed that Interact outperformed the baseline. If you're interested, please stop by our poster number 42. Thank you.
Hi everyone, I'm Hemant and I'll be presenting my work RoboCube, efficient control condition representations from visual input. So traditional two-stage controllers for optimal control uses first prediction model and then a manual controller. So these models suffer from low prediction quality, which can result to poorer control methods and are generally sample inefficient. In comparison to that, we propose a model with linear task space with spectral Koopman, which is trained in end-to-end fashion with RL. We see that these models learn better representations and are generally sample efficient in compared to the two-stage networks. And plus, they have this parallelized latent prediction, so you can implement this on hardware very fast. And on an average, we see that our model has very good performance on 6 tasks, and we see around 143% improvement in the performance. And these are, in general, very robust as noise and external disturbances. Thank you.
Hi, everyone. My name is Chris, and I'm happy to share our work today. When state-of-the-art generative policies are deployed in the real world, they will inevitably encounter scenarios that cause them to fail in unexpected ways. In this work, we ask, how can we detect unknown failures of generative policies at test time? We propose the Sentinel runtime monitoring framework. Constructing Sentinel requires only the generative policy, a handful of successful rollouts, and a language description of the task, after which it automatically calibrates its failure detection parameters. At deployment time, Sentinel monitors the temporal consistency of the policy, raising an alarm if the policy's action distributions change more than they normally would throughout a policy rollout. Sentinel also performs video reasoning with vision language models to detect when the policy is failing to make progress on its task while being temporally consistent. We demonstrate that our approach detects 97% of diffusion policy failures across simulated and real-world experiments. If you're interested in learning more, come see me at poster 44. Thanks.
Traditional driving pipelines struggle with omitting rare objects and their unique attributes and neglecting the decision-level interactions between objects and vehicles. Therefore, we propose Drive VLM to utilize a vision language model to perform a chain-of-thought reasoning for planning, including scene description, scene analysis, and hierarchical planning. For deployment, we also propose a dual system to leverage the strengths of Drive VLM and traditional autonomous driving pipeline. To construct the training dataset, we propose a comprehensive data mining and annotation pipeline, including mining, selection, annotation, and verification. Drive VLM Dual achieves SOTA performance on the new scenes dataset and our proprietary dataset, and our 2B parameter model runs at 3 Hz on the ORNX platform. To demonstrate the effectiveness of our dual system, we deploy it on a production vehicle and test it in various real-world scenarios.
Hey, I'm happy to introduce getting robot policy learning via zero-shot labeling with foundation models. Normally, language condition imitation learning policies are trained by collecting demonstration data, followed by hindsight relabeling through human annotators, and finally, language condition policy training. However, the hindsight relabeling step is expensive, so we ask whether we can automatically perform hindsight relabeling without requiring any annotated data in the first place. We propose NEALS, a framework that leverages recent state-of-the-art foundation models to segment long horizon demonstration data into key states and corresponding language annotations without requiring any model training. We evaluate our framework on a large-scale, diverse manipulation data sets, and we show that we can produce key states and corresponding language annotations while only requiring RGB observations. We also show that we can train language condition policies with the artificially generated labels that perform on par with policies trained on crowdsourced annotations. If you want to know more, please come by our poster. Thank you.
Hello everyone, I'm Haran from Berkeley, and I will present our work, DQ-ROMA, a novel stereo depth estimation method based on diffusion models. Our model handles major depth sensing challenges, including ambiguities and challenging materials. Our disparity diffusion-based depth sensing framework takes the raw disparity map and the left-right stereo image as input, and is further guided by the geometry prior to the stereo matching. The gradient for the target disparity distribution consists of two terms, the learn score function and the geometry gradient obtained by taking the derivative of the stereo matching loss. And our method predicts the clear object boundaries, while other methods struggles with transparent and specular objects. And here are some point cloud visualizations of our depth estimation results compared with raw interior real sense cameras. And it also works well for fixing the robotic symmetrical gap. Thank you so much.
What would it take to scale up robot learning to truly useful tasks like folding laundry while also minimizing human effort? Well, training imitation learning for something like this requires a massive human effort for data collection, whereas autonomous methods like RL require human effort on environment design for things like resets and safety, which has limited its use. We study a class of methods in the middle of this spectrum, autonomous imitation learning, where we train a policy on human data as well as its own successful rollouts and see if we can reduce total human effort. We encounter a variety of environment challenges in setting up truly autonomous data collection, which result in our simplifying tasks to be less useful. So environment design costs are systematically hard to reduce. We then study a variety of methods in making use of autonomous data, but find only mild performance gains, indicating that our effort was better spent just collecting more data for standard imitation learning. Thanks, and come to our poster for more detail.
Hi everyone, my name is Jun Bang, and I'm excited to present our work to imitate real-world visual motor policy learning via video generation. Given a visual observation of the scene, we fine-tune a video model to generate video of a person performing a task with a tool. To translate into robot behaviors, we track the tool in the synthesized video and transfer the trajectory into explicit robot actions. By employing a video generative model, we find the policy to be more generalizable, interpretable, and dataset collection more scalable. We demonstrate experiments where the robot pushes previously unseen shapes to a target location in the real world. Thank you for watching, and for more information, please check out our poster or visit our website.
Hi everyone, I'm Yi Zhuo from NUS. I'll present Viper, our neural planner for visibility-based pursuit evasion. Unlike many pursuit evasion problems that assume full observability, we address a more general worst-case scenario where agents with limited sensing has no information about the environment or even the invaders. For example, a team of robots need to clear a museum after its closure to ensure no personnel remain in sight, regardless of their movements. We propose Viper, the first learning-based solution for such problems, which shows its emergent teamwork behaviors, adaptability to diverse team sizes scenarios, robustness to agent failures, and deployment on real robots. We use graph transformer that decodes and encodes it into local decisions. During the centralized training phase, we provide the network with ground truth graph, along with a credit that tends to agents individually. You can stop by poster number 50 to know more about it. Thank you so much.
Hello, my name is Mujin, and I am presenting OpenVLA, an open source vision language action model. OpenVLA is a 7 billion parameter multi-robot manipulation policy built by fine-tuning a pre-trained VLM on almost 1 million robot episodes. It is trained via imitation learning to directly predict low-level robot actions, and we do not modify the VLM architecture at all. With a pre-trained VLM backbone and large-scale robot training data, OpenVLA exhibits strong performance across various axes of generalization and outperforms baselines like RT2X and Octo on multiple robots in our evaluations. In addition, OpenVLA can be quickly fine-tuned to new robot tasks with parameter-efficient fine-tuning techniques like LoRa, and it outperforms strong baselines like diffusion policy trained from scratch. We are grateful that OpenVLA has been used in various research projects and has been downloaded around 220,000 times so far in just 5 months. Thank you so much, and happy to chat at poster number 51.
Introducing our work, context-aware replanning with pre-exposed semantic map for object navigation. In map-based navigation, information retrieved from map is not always correct. The user can ask a robot to try again, but the robot still fails due to imperfect map. The grounding model used in these training-free semantic maps can fail due to label confusion or disparity like occlusion or noisy backgrounds. We propose to use uncertainty measures such as entropy and feature standard error along with retrieval score to improve replanning performance. Our method consists of a two-stage retrieval pipeline. With our method CARE, the replanning performance is significantly improved by leveraging uncertainty measures. Thanks for listening. If you're interested, check our website and paper for more.
Hello, I'm Eugene, and today I will talk about manipulation policies with conditional flow matching. Diffusion models achieved groundbreaking results in robotic manipulation. At the same time, conditional flow matching was recently shown to outperform diffusion models in various domains, such as images, proteins, and video generation. So in this work, we present point flow match, a novel imitation learning method based on conditional flow matching. We investigate three key design choices: the point cloud observations, the conditional flow matching framework, and the representation of 3D rotations. Compared to the baseline, we achieved a higher success rate. Our main evaluation is carried out on RL bench, and which demonstrates that our end-to-end policies are able to successfully solve complex manipulation tasks. We also test point flow match on a real Franca robot, demonstrating the applicability of our method to a real robot setting. To learn more about our work, please visit our poster.
Robot learning requires lots of data. The typical access for scaling data in the pursuit of large quantities of data is human teleoperation. But human teleop data is expensive to collect. For 1 hour of human effort, only 1 hour of robot data can be collected. We propose a new access for scaling data, autonomous data collection. We present SOAR, a way to bootstrap a pre-trained instruction following policy to scalably collect and subsequently learn from autonomous data. The data collection procedure looks like the following. A VLM proposes a task to be executed, and then a goal image is synthesized. And then finally, a goal following policy predicts actions. This process repeats, resulting in a data collection procedure that looks a lot like the robot playing with this environment. And this scales very well. We can have a fleet of 5 WidowX robot arms collect data overnight and collect 30K trajectories in just a few weeks. And finally, when we retrain the policy and all of this purely self-collected data, we find that policy performance doubles. If you're interested in learning more, come find us at poster number 54.
Hi, I'm Dalet. Today we are presenting a paper on learning transparent reward models. Reward design is hard. It requires human effort and yet prone to errors. In typical IRL, we still need to specify which features to use for the reward. Then again, we face the same challenges. Some exciting works around reward learning without human supervision includes adversarial, imitation learning, or maybe asking VLM to do it. But what about learning reward functions that look like this? In compact and transparent form, we can see which state features are used and how are they used. To achieve this, we employ old but gold max entropy formulation for inverse RL. We first select which features to use, and then we learn their corresponding weights. As a bonus, we also get reward function that is disentangled and stationary, meaning that we can train standard RL algorithm from scratch until convergence. To discuss more, please find me.
Optimization of complex motion control is both online safety critical and high dimensional. Our target applications includes the control of human neuromusculoskeletal systems in both simulation and real experiments, where existing safe optimization methods are infeasible. We propose a safe Bayesian optimization method for efficient safe optimization over high-dimensional control problems. We design local optimistic safe optimization to guarantee probabilistic safety. We utilize isometric mappings to enable safe optimization under dimension reduction. In the simulation experiment of high-dimensional safe control, HD SafeBO successfully optimizes the control of a 55 muscle model in one arm. In the real clinical neurostimulation experiment, HD SafeBO successfully improves human motion control. Thank you for watching.
Hi everyone, I'm Yorgos and I'm excited to present towards open world grasping with large multimodal models, where we study visual prompting schemes for transferring the internet-scale knowledge of VLMs to the open world grasping problem. In particular, we draw visual markers and exploit the OCR capabilities of VLMs to ground objects based on referring expressions, produce grounded manipulation plans for decluttering, and select grasp poses in order to avoid collisions. We combine these three components in an integrated system that can be applied zero-shot in novel tabletop domains and enable closed-loop planning such that the robot can recover from failures. We show that VLMs can advance the performance of zero-shot approaches in complicated, cluttered scenarios, and in particular, they excel at grounding objects based on open-ended language inputs, such as object states and attributes, spatial relations, user affordances, and others. Find us at poster number 57, and thank you for your attention.
All right, everyone, let's now give let's all thank our speakers. Just a quick announcement. Right after the poster session, there will be the keynote session. I encourage you all to come. Go have your break. Thank you.